Now that we have seen what is an interactive proof and what is a probabilistically checkable proof, I'm ready to explain you what is an interactive oracle proof. Actually, it's the combination of both. Note that an interactive proof has interaction but isn't necessarily succinct, whereas a probabilistically checkable proof is succinct but isn't interactive. So the idea of an interactive oracle proof, an IOP, is to combine both things. So in a theoretical setting, again, the verifier's access to the proof is modeled as an oracle or several oracles which are sent in each step by the prover. Note that the oracles are sort of necessary to make sure that a large proof is sent to the verifier to which the prover only has very restricted access. So in a practical setting, this oracle is substituted by a vector or by a polynomial commitment string. So if you look at the following diagram, which is kind of a high-level sketch of an IOP, or if you wish, its implementation, a SNARK. So in the first, we have here X, which is the statement. The W is kind of the secret now. It's not sent to the verifier in this context. Or maybe it is, but we are not clear about that for the moment. This is about privacy, which will be addressed in the next module. But as a function of X and W, the prover will produce a first oracle, which will be sent to the verifier. The verifier now issues a challenge, and then as a result of the challenge, the prover will open parts of the oracle, part of the commitment, if you wish, and this process repeats. So this is the high-level idea of an IOP, and is always the high-level structure of a SNARK. So you must think of a SNARK as an interactive protocol between the prover and the verifier. Now, you should also know about the Fiat-Shamir transform. So here it's almost similar to the previous slide. The notation now, it's not F, it's M, but it's the same thing. Now I'm going to explain to you how to transform any interactive proof into a non-interactive proof using the Fiat-Shamir transform. The idea is the following. If you look, for instance, here at the first step of the verifier, V1, V1 uses as its input all the messages that it has seen before. I call this the transcript. It's the transcript of the common reference string, the statement X, and message 1. And so as a function of these inputs, the verifier is going to decide to accept or reject. If it accepts, it will go on with the protocol, will send out the challenge. The challenge gets sent to the prover. The prover will use his transcript, which is called TR2, which includes everything that's been sent before. And as a result, we'll create a new message, etc., etc. Now, in the Fiat-Shamir transform, what we are doing is the following. Instead of the prover receiving a challenge from the verifier, the prover is going to create its own challenge. You can see this here. The challenge here, C2, now will be the hash of the transcript of all the messages that has been sent so far. So what you see here in the middle, it's only conceptual. It's not there. It's to make the relation clear between this slide and the previous slide. But it's not there. The things between brackets isn't really there. So what happens is that the challenges that are, in this case, the challenges are created by the verifier. They are created by the prover himself based on all the messages that have been sent so far. So we have here C2 is the hash of the transcript up till that point. We got C4 is the transcript up till that point, etc., etc. So this is essentially what the Fiat-Shamir transform is doing. The proof generated by P is now the sequences of messages that you see in the middle. You don't even have to include you could even leave out the challenges, because the challenges, they are determined by, they are a deterministic result of the messages. So if you wish, you can even leave out the challenges C from the proof. And so the proof becomes only the messages that we see here, X, M1, M3, M5, etc. And so what the verifier does, so conceptually we can think here as the channel sending these messages to the verifier. The verifier will get the proof as one message, one block, and it will go through all the same steps that it would have gone in the original case. So this is the Fiat-Shamir transform, and all the time when we are saying that we are using an interactive protocol, you must always keep in mind that as a last step, we will make it into a non-interactive protocol. So this is very important to keep in mind when discussing SNARKs. Now you must be aware that the security of interactive and of non-interactive protocols, they are not equivalent. Let's say that you choose a security factor of 30. So in an online attack, the chance that the proof will succeed will be 2 to the minus 30, which is 2 to the minus 9. So that may be acceptable because that's a very low probability. But in an offline attack, in the case of the hash function, then the prover, he can try a billion possibilities maybe until he finds a special hash combination with special input to find a fake proof for the statement. So this is not acceptable, obviously, and so for that reason, in when we apply the Fiat-Shamir heuristic, you should have a very high security factor, at least 2 to the minus 80, because that is supposed to be infeasible. And as another important observation is that a Fiat-Shamir proof will be convincing to a third party. So if the prover shows the Fiat-Shamir transcript to a third party, this is convincing, because the party will realize that the verifier and the prover cannot have conspired in the randomness of the challenges. So this, just to summarize it, what we see in this module, we saw a brief outline of the power of randomness. I give you a rough outline of why probabilistic algorithms are important in general, and I give you a short introduction of what interactive proofs are, probabilistically checkable proofs, and interactive oracle proofs. So this is where we end for now.